Thanks, everyone, for being here with us today. Hope you're enjoying the conference so far. My name is Jesús Barrasa. I'm the one up there on the screen. I'm a developers relations engineer with Neo4j. And for the next half hour, I'm going to be talking a little bit about some similarities and differences between RDF and the property graph. Let me start with a very quick show of hands. I mean, do we have RDF users in the room? Some of them. Great. I see some familiar faces. So some of you have already listened to a part of what I'm going to say today. I'll split the talk in basically two parts. So the first part is going to be a bit, kind of educational in the sense that I'm going to explain for those of you who are less familiar with it, how the two models are similar and how they're different. And the second part, I'll be a bit cheeky, and I'm going to try and rebate some of these misconceptions that I keep finding, published by all sorts of vendors, analysts, and that I have the impression that are confusing the people who approach graphs for the first time. So, yeah, that's me. I'll start with a quick refresher of what both the RDF model and the label property graph, that's LPG, what they are and where they come from. So the basic idea is they both model the world as a graph, so they have this abstraction in common, but they do it in slightly different ways. So let's start with RDF. RDF is a recommendation from the W3C, pretty much like HTML, like XML, CSS. And it's a recommendation it's a model for data exchange. So it was conceived as a way of exchanging data on the web. It was published at the end of the last century. And it became quite popular when Tim Berners-Lee and James Handler and Aurel Asila published this article in Scientific American around the same time, and they described the vision of the semantic web. At the time, the web was very different from the one we have today. It's probably Web 1.0, something like that. But it was a lot more static, a lot less APIs. It was a lot more based on pages and for human consumption. And their vision was, let's try to publish data in a way that's more structured, better semantically defined, so that agents, as they call it at the time, software robots, can use it in order to do some intelligent tasks. So that was the vision of the semantic web. And they put RDF at the center because that would be the way to describe data. So that's where it comes from. It's all about interoperability, publishing, exchanging. But then, of course, persisting data became a thing, and a specialized type of store appear, which is a triple store. We're going to see in a minute why it's called a triple store, RDF store. It's a type of NoSQL database that specializes in storing RDF data. And they exist up till today. They somehow changed their names, and they still call themselves semantic, but they've picked up a little bit of this popularity of graphs. So you will see them calling themselves semantic graph databases. We're going to try to understand what that means. Then on the other hand, the label property graph is the model behind Neo4j. And it comes from, for a more detailed story, I would recommend you go to YouTube and watch this video by our chief scientist, Jim Weber, where he explains where it all comes from. But basically, again, also at the beginning of the century, this group of engineers in Sweden were working on a content management system, and they were dealing with this problem of working at the application layer with objects, connected objects, relationship between things, and having to store that and persist it as tables in a relational database. So it all evolved, and out of this came out what today is Neo4j, a native graph database. So as I said before, they both have in common the fact that they model the world as a graph, but in slightly different ways. A graph, as we all know, is composed of two main elements: nodes or vertices, and relationships, connections, edges. Let's look at what the RDF graph looks like. RDF is a logical model, so it's based on the notion of statement. And statement is an assertion, is a little sentence with a subject, a predicate, and an object. So it's all broken down in atomic triples. That's where the name comes from, like this one. So I'm describing a person that I identify with this URL, people, :/Anne, and I say that she's a person. We're stating that this resource, this thing, is a person. That's a fragment of my graph. This is a person. I'm also saying that she has a user ID that's @Anne. So I'm adding another statement, another triple, another assertion about the same resource, and I'm starting to build another edge to the graph, and so on and so forth. I can keep adding that she has a name, and that there's another person, another resource, that likes Anne, right? So it's based on this idea of breaking down every statement into atomic facts. So it's an atomic decomposition of your data model, and that creates a pretty dense graph. Now, in there we see the nodes and the relationships, the vertices and the edges. But if we look at the label property graph, we don't talk so much in terms of statements, but we talk about objects, objects connected to each other. And by object, I mean a thing that has an internal structure, that has some attributes, that has some properties. So I've tried to phrase it a little bit in English, but the idea is we describe a person that's described by her name, her user ID, and her globally unique identifier. And all that is a node. So as you see, it's just one node, but it has a set of properties. And it has something that we call a label, a type. So instead of breaking it down in individual statements, we have a richer structure. We say that there's another person, exactly the same example that before, that's Dan, and Dan likes Anne. As you see, the result is significantly different. It's a much more compact graph, and that's because part of the information is not modeled as a structure, as a graph structure, but as the internal structure of both nodes and relationships. I've included the date there. It's not in my data, but it's just to emphasize the idea that both nodes and relationships can have internal structure. So we have, in a way, the flexibility to decide what do I want to model as the internal structure of a node, and what is a structural connection with other node. So these are the basics of what the two graphs model look like. So if, again, we see the vertices and edges, and if we compare them, I think I've reiterated that enough. So where the vertices come from, every statement will have subject and object being vertices, and the edge will be the predicate. No element in that graph has any internal structure whatsoever. It will be either unique identifiers representing entities or literal values, as they call them, for values or properties. Whereas in the label property graph, nodes and vertices and edges, can have, on top of the unique ID, can have a set of key value pairs that describe their internal structure. So both elements do have internal structure, right? Different models, they're queried in different ways. So they have their own query languages. Since RDF is described in terms of triples, in terms of statements, the query language is also a triple pattern language. So I'm trying to answer that query on the top. Who likes a person named Anne? And what I'm going to do is say, well, there's a resource that I call A that has a type person, so it's a person. This resource has a name. The name, I want it to contain Anne, because I'm looking for Anne. And once I found this A, I'm looking for someone that I call who that likes A. So I'm breaking that down in statements. And the result of my query will be who. That's what There's also a section where I define prefixes, and that's because every named thing in a graph, in an RDF graph, is uniquely identified by a URI. As I mentioned before, it was all about interoperability, so naming things in a unique way is crucial so that then you can do things like integration and, as we're going to see, inferences as well. On the Cypher side, Cypher is the query language for the property graph, or the label property graph. It's ASCII art based, so I'm drawing with parentheses representing nodes and arrows representing edges, connections. I'm drawing the pattern that I'm looking for. I'm saying I'm looking for someone who likes someone, and this someone is called Anne. The restriction, the filter is very much SQL style, and the pattern, as I say, is ASCII art. Good. Another refresher so far. I hope that's, for those of you who are less familiar, has clarified a little bit what we're talking about. Now I'm going to look at this misconceptions that I keep finding, that I keep hearing from prospects when they talk to us, and that I hate, and I want to at least give my opinion. Didn't mention at the beginning that before joining Neo, I'd spent a few years, well, did my PhD in the semantics in the RDF world, and then spent a few years using it in the telecom space for a company here in London, and modeling basically network topologies and answering questions like impact analysis and root cause analysis. So I can say that I have a decent view on both sides. So the first one, RDF versus graph databases. So when I read RDF versus graph databases, my first question is, what are we talking about? Hang on. Is it the model or is it the store? So far, I've explained you what the models look like. I haven't talked about stores. These models are persisted, right? And we have we have Neo4j as a good example of the label property graph, and we have a number of triple stores. So the first distinction that we have to make is this one. Let's separate the model from the store, because we're going to see in the next slide that RDF is a data exchange format. So I can store my data in a label property graph, or in a relational database for that matter, and expose it, exchange it, integrate using RDF. So when we compare, it's important to differentiate that. And then we can look at the stores. And there are very important differences as well. RDF stores, if you think of a triple, the standard way of storing it is a table with 3 columns, as simple as that. There will be optimizations, there will be indexes, there will be ways of making it performant, but basically it's very, very strongly index-based, which means that we're joining, which means that if you're doing a deep traversal, you will be hit by the join problem. At the other end of the spectrum, we have the label property graph, Neo4j in particular, Neo4j's implementation, which is a native graph, which means that connections between nodes are persisted in disks. And they're actually pointers between elements. So we're not scanning indexes, we are chasing pointers. So very, very different approach to storing and, of course, querying the data. With a lot of implications, of course, from the point of view of the performance, in the case of deep traversals, and also the predictability of the performance. If you're thinking of a traversal that's based on chasing pointers, not only performance is great, but it's also predictable because you're not affected by the overall size of your model, of your graph. You're only affected by the portion of the graph that you're traversing. Good. Also, historically, RDF stores were never meant to be used in transactional scenarios. So they were typically knowledge bases, data set where information is additive or very slowly changing. Whereas Neo4j, which is obviously the store we're comparing it against, is a transactional database. It's made to take highly dynamic models and have reads and writes and high throughputs. So there's a number of ways in which we can compare stores, but the key idea here is let's separate these two. One thing is the model and one thing is the store. And as I was saying before, and I want to do a micro demo here, I want to put my hands on some code just for a second, I want to emphasize that. So RDF is the way we exchange, we publish data if we decide to do it using RDF. But it doesn't matter how we store it. And what I'm going to do is, I came up with this idea a few months ago, which is, I called it the Turing test of RDF-ness. So a Turing test, if you remember, is something like to what extent a program was able to show human behavior to an external observer. So what I'm going to ask from two systems, one is a triple store and one is Neo4j, can I ask you a question in a way that you send me a response that's RDF to the point that I won't be able to tell who's behind? Well, if I manage to do that, I think I would have proven the fact that model and store are two things that are separate and independent. Good. So what did I do? I went to the British Library, to the website, and looked for a book. Found this one by Emil, Jim, and Ian, Graph Databases. So the British Library, they offer an RDF endpoint. So I can take the ID of this book, which is down here, this system number, and I can go to this endpoint and send a HTTP request, which is what I'm going to do up here. If you see, it's not very readable, is it? I don't know if it's any better. So what I'm sending, as you see, is an HTTP request to an endpoint with the URL. What comes after the describe is the URL, which is the unique identifier of the book that I was showing. So if I run that, the endpoint is going to send me a few triples. There we go. And the triples are statements pretty much like the one I described before. They're proper URLs, but you see that the book has a title, a description, an ISBN number. It's connected to Jim Weber down here, to Emil. That's all the database, or all the triple store. I can't tell which triple store is there. I know that it can be queried, that's all. But that's what my British Library endpoint returns. Now, what I'm going to do is go to my Neo4j instance running here in my laptop, and I'm going to use a store procedure that, hang on a second, no, that's not what I want to do. That's the call. That just takes the URL, pretty much the same one. You can see that the URL is the same that I use up there. I'm sending a describe request to the same endpoint, and I'm going to ingest these triples and bring them into Neo4j. If I run that, and the connection works, it's telling me I've loaded these 23 triples in Neo4j. Now, just to show you what it looks like in my browser, I can run a quick query and show you that I have the graph databases there. And again, let's make it a bit bigger, but we have the book at the center, connected to a number of entities, and if I look at the properties, there's been a bit of a transformation, because as we saw before, we saw that properties in the property graph are part of the internal structure of the node. So I've transformed some of these triples into properties of the node, but the connections remain as relationships. So that's it. I've loaded this fragment into Neo4j, and what I'm going to do now is send the same request to my Neo4j instance, hoping that it will give me back the 23 triples that the endpoint of the British Library was giving me. In order to do that, I'm going to leave my shell and send one simple request, here we go, to an extension that's running, as you can see, on my local host 7474. So I've deployed an extension on my Neo4j instance, and I'm telling, give me all you know about this resource. And I'm calling it by its name, its unique URI. And if all works right, I get 23 triples, exactly, probably in different order, but I'm getting exactly the same information that the endpoint at the British Library was giving me. Thank you. Well, that's a well, it's probably a silly example, but I hope that the message is clear. We can be RDF compliant, we can be open standards. I've heard all sorts of things. But Neo4j, well, there you go. You want to talk RDF? We can talk RDF. Let's separate a model from store. How am I doing for time? 10 minutes, good. Right, let's go back to the slides. So that was my micro demo. And let's continue with another alternative fact. Take your time to read it, because it's a thing. So it's telling me, and I'm going to tell who's that. If you're interested, go and Google it. It's telling me that a triple store is going to be able to figure out that one Mercedes is a person and the other Mercedes is a car, as opposed to a relational database. It takes it against databases who can't understand anything that's not explicitly told to them. First of all, what do we mean by a database understanding things? But anyway, let's make things clear. Semantics in RDF are just rules. Full stop. There's no inference, no new information, nothing is going to be derived from my triples, except whatever I explicitly tell my store to derive. As simple as that. So exactly what it said about databases, whatever they mean here, can be said, should be said about this thing up here. So semantics of RDF, just rules, is described in this thing called ontologies. An ontology is just a description of your data set in terms of our vocabulary. There's some standard languages like OWL, RDFS. And the kind of thing that I express in an ontology is something like, if something has an ISBN number, then you can derive that it's a book, right? That's what you define when you describe a domain property. That's the kind of statement. And a rules engine will take your data, find that you have an ISBN number, and if you didn't know it, I will derive that you are a book. And that works very well and makes sense in the case of distributed data ownership. If you think where RDF comes from, it was about interoperability. It was about multiple data owners, distributed, fragmented, incomplete fragments of data living in different places. So if you have a portion of the data that's not complete, this semantics could help you. Is that a question? Oh, sorry, I thought. Right. So, but semantics, I mean, nothing not explicitly declared will be derived. It's not by modeling things as RDF that your data is going to become smart. There's no magic in there. Let's make this clear. And then there's another problem, is that inferencing is just rules engine. I mean, when in a rules engine you have chaining, and chaining by chaining, I mean, if you derive new facts, new elements in your data that can trigger new rules, that can become horrible to debug. So developers just don't like it. And the other thing is from a computational point of view, computational complexity, these models are sometimes, well, most of the times, undecidable. So we can't guarantee they will produce results in a reasonable time. So I'm not saying there's no situations where you can take advantage of semantics, but let's make it clear. The key thing is explicit semantics. And just to confirm my point, there was this other vendor who called themselves the world's only triple store, only enterprise triple store. When talking about when do you do semantics, well, do it on a tiny bit of data, don't risk too much. Actually, no, don't do it. Consider an alternative. That's what they say, right? So seriously, that's the reality of semantics. And there's the final, and I'm going to finish with this one, misconception. I mean, this is not a misconception, but this idea of always associating RDF and semantic web, semantic technologies with natural language processing and sentences like this one, because it's subject, predicate, object, there might be like a connection with, understanding speech or written natural language text. Well, for all of you who have tried to structure natural language and understand it and use it in any structured way, you know that there's a complicated process of parsing, lexing, eventually using some probably graph resources like WordNet, like ConceptNet. But all that is one thing. And then whether you store your results in an RDF or in another store, for whatever you decide to use, that's a completely different thing. So again, as I said in the case of the model, these are two separate things. And we have to keep in mind that they're completely independent. Yeah, I think that's the last one. And so just to conclude, let's summarize when you are approaching the possibility of using graph and you want to make a decision, I would say that things to keep in mind are these as you see on the screen now. So consider both the model and the storage separately. Try to understand how do you want to represent your data. Is it like logical statement? Is it like a property graph model like the one I showed before? Also think the kind of workload that you're going to have on your data, and then that will determine the graph that you need. Sorry, the store that you need. So keep these two things separate and figure out what's your best choice. Finally, what's the nature of your data? Is it a static data set? Is it a dynamic? Do you need a transactional behavior? Because that can drive your decision in one direction or the other. And again, ask yourself, do you need really rule-based inferencing? Because there's a number of ways in which you can make your data reactive, but understand what the semantics of RDF are before assuming, and that's the conclusion at the end. Don't make a decision based on these alternative facts, these kind of statements or assessments that we find on the web, and I find not particularly founded. That's it. Thank you very much. If you have any questions, I'm happy to take them. Otherwise, I'll be outside.